Ah, sorry. that was the first thing on the video. Is ah. Well, it just turned 2:31 instead of 2:30. I thought I was going to get started on time. This I don't think you're going to have too much difficulty with because we talked about all of this last year. So this will be a good start to this unit. And honestly, there's not a lot that's new here, but some of the solid stuff that we talk about will be a little different and will be quite a bit more in depth than what we talked about last year. But really, it's liquids and solids, and then at the very end of it, I'll hit you with coordination compounds, which that part will be a little bit. Well, I guess, okay, so liquids and solids, and then we talk a little bit more about solutions, a little more in depth about solutions. It'll be some of the stuff that we talked about at the very end of last year. Saturated, unsaturated, that sort of thing. So again, most of that will be review. And then when we get to coordination compounds, that will be completely new. We haven't talked about that at all. But the good news is I'm going to spend a day on it because I don't think they're really going to test it on the AP exam. It's kind of like organic. They're not going to test it specifically, but they're going to put organic stuff on there. And so I don't want you to panic if you see it. I want you to be familiar with it at least. So that's the one thing that'll be a little bit new. But everything else in this unit, I think this will be hopefully a good one to end on. It depends on whether you like the conceptual stuff or the mathematical stuff better. But this will be a big change from the last unit when everything was pretty much mathematical. This will be a lot more conceptual. So you'll be, at the end of this test, your hand will be tired from so much writing. So the intermolecular forces, basically we're just kind of picking back up with the intermolecular forces thing. We talked about that a little bit with the gases, but the gases, I don't know. In retrospect, I might take the gases and put them at the end of the semester instead of doing, instead of breaking this up, because we talked about intermolecular forces 2 units ago, and now we're coming back to it. It might make more sense to just keep going with it. But the intermolecular forces basically affect many of the physical properties. Sorry, hang on a second.
Yeah, then when I tried to divide by 1, it was like, oh.
Yeah. Okay, so we're back. I don't even remember what I was talking about, sorry. Yeah, that's right. Sorry. Yeah. Anyway, I was gone, so now I'm back. There you go. So we're going to talk about some of the things that intermolecular forces actually affect. One of the things that they affect is surface tension, and that's being shown here in this picture. This picture's in your book as well. But basically, the molecules get pulled in every direction. If you're talking about a molecule like down here, it's getting pulled in every direction by other water molecules. But at the surface, really the only place it can get pulled is inward and inward. Okay, it's not getting pulled this direction because there are no water molecules up above it to pull it that way. So it's all kind of being pulled in at the surface. And so you get this tension at the surface where the molecules actually don't, they're really sticking together in a certain direction. Okay, and so then you get something like a water strider. If it can spread itself out enough, then it can actually walk over the top of the water without disrupting that surface tension. So that's one of the things that can is caused by intermolecular forces. Another one is viscosity, and we talked about this last year too. I think we even did an activity where you had some liquids and they were thicker or not so thick, and then you looked at their molecular structures and tried to figure out why. I like this one because it's showing you, you can barely even see this. I didn't realize it was so light. But hexane, 3.26 times 10 to the negative fourth. Wow, that's really hard to see. 3.26 times 10 to the negative fourth. Once you get down to decane, it's 1.42 times 10 to the negative third. So much more viscous than the hexane. And the reason for that, it has nothing to do with polarity, really. It has to do, well, I suppose it has to do with polarizability because these are just London dispersion forces here. So the bigger, the longer the chain, the more viscous it's going to be. Okay? You get this chain long enough, eventually it's going to be a solid. So it's going to, you know, solids are very viscous. They don't flow at all. By the way, viscosity is the resistance to flow. So the more viscous it is, the thicker it is. Okay? And so it's related to the ease with which molecules can move past each other. If they're too attracted to one another, they don't move past one another very easily. So that's that. And then, yeah, obviously viscosity increases with stronger intermolecular forces. It decreases with higher temperature. Does that make sense? So you increase the temperature on these particles in the liquid, they start to move faster, right? Okay, if the particles are moving faster, they're going to be less attracted to one another. So I think we talked about that last year even as well. Anybody have relatives who, anybody, there's two of you. Do either of you have relatives who put their syrup in the microwave before they pour it on their pancakes? Okay. I don't know that that's because it makes it less viscous. That's probably, maybe that's why. I don't know. But it's probably just because you like it warm. But anyway, it does make it less viscous. You might have noticed that the syrup is less thick after it comes out of the microwave. So there you go. Okay, we talked about surface tension already. Phase changes. I think you know all of these except for maybe deposition. I don't think that's going to come up on an AP exam, but that's technically the reverse of sublimation. So it goes from a solid to a gas, it sublimates. If it goes from a gas to a solid, it deposes. I don't know. It deposits. No, I'm not going to ask you about deposition. They ask about sublimation quite a bit, so you need to know that one. But deposition, an example of that might be like frost. So if you have water vapor that's just skipping the liquid phase and it's freezing, that would be an example of deposition. But the rest of these, I think we know. And the states, the names for the phase changes, I think we know all those too. Technically, from a liquid to a gas is vaporization, not boiling, not evaporation. Boiling and evaporation are both types of vaporization, but the general term is vaporization. I think that's pretty much it for the phase change stuff. Change in intermolecular forces for each type of phase change. Okay, this is a little useful. And they do ask these kinds of questions. I'd forgotten this was on here. If something melts or freezes, then if you're thinking about the change in intermolecular forces that's happening there, how would you describe the change in the intermolecular forces? Okay, so it depends on whether we're talking about melting or freezing, right? Let's say that we're talking about melting first, and then we'll talk about freezing in a second. So if something is going from a solid to a liquid, what's happening to the intermolecular forces there? Can we just say they're weakening, or is there something more that we should say? They definitely are getting weaker. But if these things have the ability now to flow past one another, they're actually probably breaking a little bit, aren't they? Okay, do you remember talking about this last year? That when something forms a liquid, those intermolecular forces break and then reform, break, reform, break, reform, because you've got the molecules sliding past one another. And then they'll get attracted to another one and then form a new intermolecular force there. And so they're just breaking, reforming, breaking, reforming. And there's enough attraction there still that the liquid will hold together as a constant volume, but it's going to take the shape of whatever container it's in because it's not held rigidly in place. Okay, so when we talk about melting, you could say something like rigid intermolecular forces. I'm going to abbreviate with IM, intermolecular forces. Break. Then begin breaking / reforming as the molecules move past one another. Something like that. Okay. There are just a lot of questions in the new AP, not a lot of questions, but a lot of essential knowledge statements in the new AP curriculum that focus on intermolecular forces. This is one of the big things that I promise is going to be on the new test. So you need to know intermolecular forces really, really well. You need to know how they relate to liquids and solids and what they do. You need to know how they relate to boiling points, viscosity, surface tension, all of those things. Okay, so you need to understand it really well. The vaporization condensation thing, what's happening to the intermolecular forces when something, and now I guess I should mention, when something freezes, it obviously goes back the other direction, right? So the molecules, they're slowing down maybe because they're losing some heat energy. And as that happens, eventually it gets to a point where the intermolecular forces are strong enough to lock them in place. And then they don't move really anymore. They vibrate slightly, but they're not really moving. So then when we go to vaporization, for something to evaporate or for something to boil, what has to happen to those intermolecular forces at that point? So you've got a liquid. The forces are forming, breaking, forming, breaking, forming, breaking. To change it to a gas, yeah, they completely break apart, right? So that at that point, especially if we're talking about an ideal gas, you can assume that there is no intermolecular attraction anymore at all, okay? So you could say that the intermolecular forces completely break when something goes from a liquid to a gas, okay? Condensation would be the opposite. So you've got things that really don't have any intermolecular forces between them, but then you slow them down enough, get them close enough to one another, they start to form those attractions again. And before they actually get held rigidly in place, they'd just be sliding past one another still and start forming, re-breaking, breaking, reforming those intermolecular forces, okay? So that's kind of the idea of what's going on there. One of these days I'm going to find a good animation on this, and then I don't have to... So for sublimation, okay, so actually a good example is something that does sublime or sublimate. I never know which way to say it. Carbon dioxide, right? So you got carbon dioxide. It's completely nonpolar. It's not that big, right? So not a lot of attraction of the particles for one another. So if you have it in a set of conditions where you have pressurized it so much and gotten it so cold that it actually does solidify, as soon as you put that in a normal temperature environment, normal pressure environment, these things are not going to be that attracted to one another anymore. The attractions just are not very strong, so you get something that just skips the liquid phase altogether because of its weak intermolecular attractions. You put it in normal conditions, and it's just going to go straight to a gas. Okay, those intermolecular forces will just completely break. So that's what's going on with something like dry ice. Most things that sublimate are that way. So I'm trying to think of another good example of something that sublimates. I'll have to think about that. Nothing's coming to my head at the moment. I know there's some other ones, but I would imagine we could say about all of them that they have fairly weak intermolecular forces, and that's why that happens. Okay, so there's the sublimation. Oh, good question. Sublimation deposition. And again, I guess just to reiterate, can't talk. So tired. Reiterate what I just said. Sublimation is basically, those intermolecular forces are so weak that you've got something that's a solid and the forces just break completely, okay? They don't bother with the whole breaking, reforming thing. They skip that step and just go away as gas molecules, okay? The energy change is associated with change of state. Now we're kind of back to the delta H thing for just a minute, okay? And that's, I guess that's one place where we will have calculations in this unit, is with the delta H. Now, I just want to point this out. So we've got butane, not that big, completely nonpolar. So it makes sense that it would have a low heat of fusion, low heat of vaporization, right? Now, what is heat of fusion? Do you remember what that means? I think we talked about that in an earlier unit. Very briefly, though. Yeah, it sounds like fusion. It sounds like something's fusing. It's really kind of a deceptive term. I don't know why they call it that. Heat of fusion really is how much heat does it take to melt a solid. Okay? So just kind of backwards. I don't know. But heat of fusion, how much heat does it take to melt a solid? And then heat of vaporization, how much heat does it take to vaporize it? Now, one thing to notice, on every single one of these, the heat of fusion is significantly smaller than the heat of vaporization, right? And that kind of makes sense because to vaporize something, you have to break the intermolecular forces completely so that they're free of one another, okay? That takes a lot more energy than just loosening them so that they're, breaking, reforming, breaking, reforming. But the other thing to notice here, butane has the lowest heat of vaporization, or lowest heat of fusion, lowest heat of vaporization, because it's the easiest one to get to turn into a gas, okay? Because, again, it's nonpolar, it's not all that big, okay? So that one will change into a gas at a lower temperature, or you'll have to add less heat to it. The diethyl ether, now you've got something that's a little bit polar, okay? It's still not all that polar, but it's a little bit polar, so now you've got a little bit higher of a melting and a boiling point. Water has hydrogen bonding, so obviously that's going to be it's going to take a little more energy to vaporize or melt. And then you got mercury. What's mercury doing over here? Why does it have such a high melting point / boiling point, or a high heat of fusion, heat of vaporization? It's not really because it's large, because you might look at it at first and you might be thinking, oh, this only has London dispersion, right? Well, and this is another thing we're going to talk about more in this unit that we didn't talk about so much last year. That's a metal, okay? So there's a special kind of bonding that happens with metals called metallic bonding. Now remember, that's like the hippie commune that I told you about last year, okay? We just briefly touched on it, but that's where you've got these things kind of lined up and they're sharing their valence electrons between them. So the attraction of the valence electrons for all those nuclei in the metal atoms, that's what causes every metal except mercury to be a solid at room temperature, okay? So even though mercury is a liquid at room temperature, it has a little bit weaker attraction than most of the other metals. It's still got a stronger attraction than anything that's, covalent, that's just attracted to the molecule next to it, okay? So those metallic bonds are usually a little bit stronger, and that's why the mercury has so much higher of a heat of fusion, heat of vaporization, okay? Okay, so that's just heat of fusion, heat of vaporization. And then you guys remember these diagrams from last year? Okay, so you might see something like that again on an AP exam where they ask you what's going on here and what's going on here. And why is this one so much longer than this one? Okay? In other words, why do you have to add so much more heat in order to get D to E to happen than you do to get B to C to happen? So what is happening in the flat portions? What's going on there? Okay, well, so they're absorbing energy, but the temperature's not changing, right? Okay, so their kinetic energy's not changing. So where's all that energy really going? What's it being used to do? Breaking intermolecular forces, right, or intermolecular bonds, not covalent bonds. Okay, so you're not, with water vapor, you're not breaking the bonds between the hydrogen and the oxygen. Okay, not this bond. You're breaking the bonds between water molecules. And so that's where that heat is going at that point. From A to B, you're adding heat, and it's causing the molecules to move faster. Okay? From C to D, you're adding heat, and it's causing the molecules to move faster. Anytime that the temperature is going up, the average kinetic energy is going up. So now the particles are moving faster than they were before. But at some point, that energy gets turned, instead of making the particles move faster as far as their kinetic energy, the energy starts going into breaking these intermolecular attractions. Okay, so that's why you get this flat portion for a while. And again, it makes sense. B to C is so much shorter because that's just going from a solid to a liquid. Okay, heat of fusion is a lot lower than heat of vaporization when you're going from a liquid to a gas. Okay. Temperature of the substance does not rise during a phase change. So you need to be able to explain why that happens. At which point on the heating curve does the greatest amount of liquid water exist? Right at which point? Okay. So right here, that's when all the ice is melted, and now we have liquid water, right? Now over here, and anywhere in here, some of this has already evaporated, okay, or boiled. So the point where we have the most water is right here at point B, okay? And then here's a sample problem that we won't work through now because we've got some of these that we can do for practice in class. And actually, we've done one like this. We may have done this exact one. So we definitely won't do it. But do you remember doing this where we had to change the temperature of the ice from negative 25 to 0 and figure out how much heat that took? And then the heat of fusion, how much heat it took to liquefy it, and then heat it up to 100, and then vaporize it, and then heat it up to 125. So you've got to do all of those steps and basically add them together. So we'll practice one or two more of those just so you get the idea of how that works, because you might get a question like that on the AP exam. Okay? Vapor pressure. I forgot about vapor pressure. I thought we were done. Okay, really quick here. Vapor pressure is caused because you have a liquid, and that liquid, some of the molecules at any given temperature will have enough energy to escape. Okay, so that's why we have to take into account the vapor pressure of water, even at room temperature, because some of that water will evaporate. As the temperature goes up, obviously the fraction of molecules that have enough energy to escape goes up as well. So this is another kind of one of these distributions, kind of like we had on the test today. At the lower temperatures, you have fewer molecules that have the kinetic energy that they need to escape. I mean, it's actually right here. Anything past there would have enough energy to escape. You raise the temperature, now you've got all of these particles that have the energy to escape. Okay, so it goes up. And then eventually you get it to the boiling point, and all the particles have enough energy to escape. So something called equilibrium vapor pressure. What's going to happen here, if you put a liquid into a bulb like this, it's going to start to evaporate, especially if it's something like ethanol. And it's going to evaporate until it reaches its equilibrium vapor pressure. Okay? And what's happening at equilibrium vapor pressure is these molecules are evaporating at the exact same rate as other molecules are condensing. Okay? So at that point you get no net change, and you've reached your equilibrium vapor pressure. So if you're watching this on a graph, right here your pressure, it's going to be low. As the ethanol starts to evaporate, you're going to see this, but then eventually it's going to level off, and you're going to end up with something like this, because at some point the pressure will stop rising in the container because it's reached its equilibrium vapor pressure. It's not going to go any higher than that. Okay? The vapor pressure of a liquid does not depend on surface area, just temperature. Okay, and they've tried to trick students with that in the past, so I'll give you some practice problems about that. But basically, the one thing, you just need to remember this, the one thing that you need to be thinking about with vapor pressure is the temperature. If you increase the temperature, you increase the vapor pressure. Decrease the temperature, you decrease the vapor pressure. Okay? There are lots of other things you can change that won't have an effect on the vapor pressure, but the temperature will. Okay, that's the major thing. And then the boiling point of a liquid is the point at which the vapor pressure equals the atmospheric pressure. Okay, so you've got right here at 100 degrees Celsius for water. That's when the vapor pressure pushing up on the atmosphere is equal to the atmospheric pressure pushing down, and that's when it will boil. Okay. Normal boiling point is the temperature at which the vapor pressure is 760 torr, because that's atmospheric pressure. Okay. Good grief. Okay. No, we're not going to do that because we need to stop. Just so you know, phase diagrams are not in the new AP exam. Remember these things with the triple point and all that? They say that they assume you've already learned that by the time you get to second year chemistry, so they're not going to put it in the test, so we're not going to talk about it again this year. So that's why we're skipping section 11.6, because that's about phase diagrams. Okay, that's it. Sorry, that one went long. We'll see you guys.